Hello, and welcome to this instance of the Stories lecture series. This talk will focus on digital tools for accelerating innovation in energy storage. My name is Dr. Simon Clark, and I'm a senior research scientist for battery digitalization at SINTEF in Trondheim, Norway. I've been working in the field of model-based design tools for complex systems for the past 16 years, and I'm active in the European battery research and innovation community, as well as a contributor to many open source battery digitalization resources. I work at SINTEF, which is one of Europe's largest independent research organizations with more than 2,000 employees developing, as our motto puts it, technology for a better society. So the target audience for this talk are people who are working in the energy storage field, and maybe you have some data that you want to get more value from. Maybe you want to gain more insight into some systems that you're working with. And ideally, you would have some background in digitalization fundamentals, like data management, maybe a little bit of programming in a language like Python. And the intended outcome of this lecture is that viewers should come away with, first and foremost, an understanding of the role of digitalization in energy storage and a practical overview of some semantic data and simulation resources. But we only have so much time here today, so at the end I'll provide you with additional resources to further apply the digital tools that we'll go over and support innovation. The talk today is structured into four broad topics. We'll start off with a general overview of digitalization. What is it and why do we do it? And then we'll have a look in detail at a couple of sub-aspects, including linked data and virtual environments for energy storage. In the end, we'll wrap it all up and examine how we can move from digitalization to innovation. So let's start with an example that really highlights the power of digitalization to create impact in a scientific field. The 2024 Nobel Prize in Chemistry went to the developers of AlphaFold, which is an AI tool that predicts protein structures. And this was important because understanding the 3D structure of proteins is notoriously difficult, and it's also critical for drug discovery and disease understanding. And although AlphaFold was an incredible advancement in the field, it was actually made possible by decades of vision and good implementation of digitalization policy in the field of bioinformatics. For more than 50 years, the field of bioinformatics has really been a leader in embracing digitalization as a transformative tool for the field. Already back in 1971, more than 50 years ago, they've been promoting an open data infrastructure through the Protein Data Bank that provided a centralized open access repository of protein structures. But they didn't stop there. They actually then took it one step further and started to adopt very early on the concept of semantic interoperability. The protein ontology and the gene ontology are semantic resources that allow researchers to describe data in a standardized and meaningful way. Furthermore, they have platforms for computational benchmarking, which provide an open way to work across the community and benchmark progress in a clear and measurable way. So for us in the energy storage field, we can look at the success of the bioinformatics domain and try to learn from what they've done to help build the next generation of energy storage technology. So what is digitalization and why do we do it? Well, digitalization is the process of transforming activities that were once analog or manual to use digital tools, making them faster and more interconnected and often automated. We do this because it helps us to work faster, to extract more value from the information that we have, and to make better decisions. So one common misconception may be that digitalization is just scanning things, taking paper and putting it into PDF format. But digitalization also means including searchable and structured metadata describing our resources. Another misconception may be that digitalization is just putting things in Excel and using that as a database. But good digitalization activities utilize cloud-based databases that are scalable and support advanced querying. Similarly, we may be tempted to, just kind of slap QR codes on everything, which is fine. But actually linking a QR code to a unique identifier that provides context and actionable data really takes it the extra mile and gives it value. Finally, in the world that we live in, there's an app for everything. Apps are very popular, and building an app front end is a good policy. But it also helps to connect to a robust back end that supports data management and flow across systems. So the point that I'm trying to make is that the real value and challenge of digitalization lie in creating a cohesive system where every component works seamlessly together. It's not really something that we can solve with one single silver bullet, but it takes a lot of different components all talking to each other, all working together. So all the way at the beginning, starting with good data described by metadata, stored in a scalable and queryable database with interoperability and semantic layers describing the meaning of what's there. We can then start to combine that with analytical and simulation tools, automation and workflows, and link it together in a continuously improving system that helps us to extract more value and understanding from our systems. So my talk today is going to basically cover these aspects, but for the sake of time, I'll break it down into two components. So the first is discussing linked data, and the second is discussing virtual environments and how we can apply these in the field of energy storage. So first we'll cover linked data. Linked data is a way of structuring and connecting data on the web so that it can be understood and used by both humans and machines. And the core idea is to publish each piece of information as a node in a large network graph that agents can traverse to find more information and maybe infer new relations among different things. And this may seem like a new concept, but actually you use this every day. And one good example is a social network. So if you're on a social network site, you may exist there with a profile that has some unique identifier that describes you as a person and how you're linked to other people. So maybe on this platform, you're connected to your grandmother who likes some cat videos, and you also like cat videos. So when your grandmother's birthday comes around, the social network may send you a reminder and say, hey, today's your grandmother's birthday. Why don't you send her a cat video? Because we know you both like that. And we can take this concept and apply it not only to social networks, but to any network. So for example, in energy or power systems, we may have some power source that's like a wind farm or a solar panel that's connected to different battery banks with different states of charge. And we may also associate different battery banks with data histories that describe their state of health. So an agent with access to this linked data graph can say, okay, I'm getting so much power coming from my wind farm. How can I best distribute this over the connected battery banks, considering their state of charge, considering their state of health, and make good decisions about that. So fundamentally, linked data is about structuring data, connecting data, and applying meaning so that humans and machines are able to understand it and act on it. So to understand how we got to the linked data systems that we have in place today, I think it's helpful to look back at a brief history of where we've come. And already, all the way back in 1945, there started to be the early ideas of how this might come together. And in 1945, Vannevar Bush published a concept for a fictional machine that he called the Memex, or the memory extender, which he envisioned as a great electromechanical device that would condense information from books or documents and provide an easy way for retrieving the information contained therein. And this was one of the early inspirations for the concept of hypertext, which was coined as a term in the 1960s as a way to describe text that links to other documents or text or media, which of course is very familiar to us today. And throughout the 1970s and 80s, there were some early prototypes of knowledge management systems kind of building on the idea of hypertext that included things like Zog or Inquire and Scrapbook. But it really all came to a head in the late 80s with the development of the World Wide Web, which was created at CERN in Switzerland by a team led by Tim Berners-Lee, and originally envisioned as a tool for research data management. And of course, today we know the World Wide Web has gone on to revolutionize, and touch almost every aspect of human civilization. But I think it's important and instructive to remember that this was originally developed to structure and manage research data. So we all know that the World Wide Web was very effective at implementing the concept of hypertext through HTML, the Hypertext Markup Language, and HTTP, the Hypertext Transfer Protocol. But Tim Berners-Lee noticed fairly early on that the early web was good at saying this document is connected to that document, but it couldn't really say much about what those documents were or what is the nature of their connection or what is the meaning of the information that they contain. And so he proposed the concept of the semantic web, which he viewed as an extension of the web where computers could understand and analyze all things that were there. And he proposed linked data as the foundation for the semantic web, which would be data that is structured and linked to other instances of data described with semantically meaningful and machine-readable vocabularies. And shortly thereafter, there were a stream of products and platforms and advances in that field. DBpedia, which is a linked data knowledge graph for general information, was launched. The big search engines like Google and Yahoo and Bing all got together and started to adopt the concept of linked data through their schema.org vocabulary. And shortly thereafter, the Google Knowledge Graph was launched, and other knowledge graphs like Wikidata continued to be good examples of how linked data and semantic data principles could be demonstrated and integrated into the World Wide Web. So what does this mean for us in the energy storage field? Well, energy storage is much the same as any other field in that we generate a lot of data, but it's not always so easy to automate the processing or the exchange or the reuse of data because it's stored in different structures with different labels, with different formats, and the process of standardizing it can often be very time and labor and cost intensive. But we can learn from the success stories of other fields and how they've managed to solve this. And one way is to provide metadata that contains semantic data markup. Now, metadata, somewhat amusingly, is defined as data that describes other data. And this is an essential part of extracting value from published data sets. So, for example, if we have some battery data that may be like columns containing voltage and time. On its own, this is okay, it's interesting, it's kind of useful, but without the associated metadata, we can't really understand what it is or what we should do with it. So by providing metadata that says like this has a positive electrode with NMC811, and a negative electrode that's graphite at a temperature of 298 Kelvin in a format of R2032, which is a coin cell, and performed on, some date. This now takes that information, which before was, just a collection of numbers, and now provides context to help either humans or machines understand what that data is and what they should do with it. Now, there are a variety of ways to express metadata, and a good way to do it is to just state metadata as plain text comments. So something like a text file or a README file. A better way to do it is to express metadata as structured key value pairs. So something like a JSON file or tabular data formats. But the best way, by far, to express metadata is as semantic markup with links to established vocabularies and ontologies. For example, JSON LD or other RDF serialization formats. And to better understand that, we can have a look at some instances of how metadata may be expressed. So continuing the example from the previous slide, here are three possible ways to express metadata. The first is just getting it out of your head and into a text file that can be accessed or read by humans and machines. So this could be as simple as just writing a few words. Hey, this is the voltage of an NMC 811 graphite battery cell, etc., etc. The problem with this is that it gives you a lot of freedom. And different people will write different things. They'll include different information. They'll say it in different ways. And if you want to process a lot of it, that can quickly become a problem. So a better way of expressing metadata is using structured key value pairs, like in this example of a JSON file. So here we can see we have a field chemistry that's NMC 811 graphite and format that's R2032 and so on. And this brings you a few advantages. First, you have a structured data model, so you can be sure that any data that's filled in here can be exchanged in a kind of standardized or interoperable way. Second, it's really easy to parse. You can automatically get the value NMC 811 graphite from the key, chemistry, and so on. But it has a problem, and that is that these terms like chemistry and format and R2032 aren't necessarily standardized, and they may mean different things to different people. Or maybe if you're not working in the battery field, you don't know what R2032 means at all. And this can create some errors in interpretation and limit interoperability. So the best way to express metadata is in some kind of semantic markup. And here we can see an example of a JSON LD file, which is JSON for linked data. And JSON LD provides us a few advantages. First, it provides a context. And this is like a dictionary. So anytime it encounters a term in the file, like battery cell, for example, it will go to this dictionary and say, is battery cell there? What does it mean? And if it is, it can understand, okay, this is, has been defined as this particular thing. Or, has positive electrode, is that in there? And it can see that it is, and this is a relationship that links a battery cell to its electrode. And by doing things in this way, we not only get the advantage that it's structured, we get the advantage that it's easily parsable, but we get the extra advantage that machines can understand the meaning of what's there in a very clear and unambiguous way. Now, at this point, I know what you're thinking, and let me put your mind at ease and say, don't panic. It's not up to you to write your own JSON LD files. I know they look complicated, and it's just one more thing to learn. But a good analogy is it's kind of like websites or web pages. Web pages are written in HTML, but when you go to make your Facebook page or when you go to post something on LinkedIn, you don't necessarily write your own HTML code. And JSON LD and RDF metadata is kind of the same way. It's the job of user interfaces and toolboxes and data management platforms to do this for you. It's your job to know that it exists and to make sure that it's used when you publish your data. So just to drive home the value of expressing metadata in structured and semantic formats, let's have a look at how machines will interact with the type of data that we provide. So in the first example, we have just kind of basic key value pairs in JSON format. And we can see that when a machine encounters this, it's able to, extract the structure, kind of see how things are linked, and break down the information in a way that's easily parsable, even if it doesn't understand the entire context and the entire meaning of what's expressed there. Let's now compare that with how a machine would process the best way of expressing metadata using semantic markup in, for example, a JSON LD format. When we provide the machine with the JSON LD, we can see that it translates from a human-readable collection of words into a machine-readable collection of identifiers. And this brings us one really big advantage, and that's that we can use these identifiers to point to other sources of information that then define the terms that are there and maybe links to other terms in other standards or in other data sources. And this provides a lot of added value in conveying not only the data itself, but actually the meaning of what it is and how it relates to other things. So finally, if we're looking for some examples of this in practice, there are a few places we can go. And I think one really good instance for understanding this and getting some more hands-on experience is Wikidata. Now, Wikidata is a knowledge graph that contains a lot of general information and is a very effective way of getting some hands-on experience. So if we look into Wikidata, we can see that there's a query service where we have access to the entirety of the knowledge graph. And if we don't want to write Sparkle commands, we can actually build our own queries using this nice query builder. So let's say we're looking for something that is a subclass of a battery, like a type of battery, with an additional condition that it has a energy storage capability of, let's say, greater than 10 watt hours. Now, because all of this information on Wikidata is expressed in this kind of standardized and meaningful way that we've been talking about, it's extremely easy to find that information. And not only the information that we were originally looking for, that here we found a cell that does it, but we can find out information about the manufacturer, and in this case LG Chem, and we can find out more information about the types of materials that are in there, like in this case lithium nickel manganese cobalt oxide. And we can see, okay, here's another resource that tells me even more about this thing. And I can go to Google and see all of the information that Google has about it. Or it can point me to Wikipedia, and I can look into all of the information on Wikipedia about this thing. And so you can start to see that even with, fairly basic semantic markup, the value is by providing an entry point into the knowledge graph that allows us to take advantage not only of the information that we explicitly state in the metadata, but also all of the other metadata that has been compiled in different sources, and really adds a huge additional bit of value to our data. Good. So to summarize this section of the lecture, linked data, especially linked open data, are the seeds that digital and AI tools need to grow. When we look at a lot of, the superstars of AI tools like AlphaFold that we mentioned, won the Nobel Prize in Chemistry, and their, more fun but maybe not as useful tool AlphaGo that beat the the world champion of the board game Go, ChatGPT, the list goes on and on. One of the things that they all have in common is that they're trained on structured data that comes from the World Wide Web, and that providing this kind of fuel that they need to be instantiated and this fuel that they need to grow, we opened the door to doing some really interesting things. So linked data itself is structured data with semantic markup that is connected to other data sets on the web, and it's designed to be useful for both humans and machines. And even though, linked data principles are relatively new to the field of energy storage and batteries and fuel cells, it's already led to an innovation boom in other domains and are foundational to the modern World Wide Web. So linked data tools are starting to become available for energy storage. Still a relatively new field, still a lot of development, a lot of change going on. But it's good to be aware of those developments, to keep appraised of new things that are going on, and whenever possible to try to adopt these approaches in your own work and help us bring the community forward. So finally, here are some additional resources that will help you get started and continue working in the field of linked data for energy storage. The first is the BATinfo documentation, which is an ontology for batteries and electrochemistry more generally, and that provides a lot of examples for how to do JSON-LD markup for different resources and different data sets. Then I've also provided some links to W3C recommendations for how to adhere to best practices for publishing linked data, and some models for describing tabular data and metadata on the web, which I find to be really helpful personally in my own work. And finally, also the JSON LD Playground, which I definitely recommend is a really helpful resource for learning how JSON LD works and also testing your own developments if, really getting into the details of JSON LD is something that you're interested in. All great resources, of course, not all of the resources that exist, but I think a good set to help you get started. So with that, we can move to part 2, which is virtual environments. So now we have all of our data, we've expressed it, we've put it in a database and marked it up with semantic terms. What can we do with it? Well, let's see. Virtual environments offer the means for evaluating multiple configurations and searching for optimized states in a way that may be costly or not feasible with physical testing alone. And we can kind of understand the place that this fits in our digitalization workflows. If we imagine that we have some very powerful AI agent that says, okay, the best configuration of your system is this, or the best design for your battery is that. How do we test it? Do we immediately go to the lab and build this thing, or do we immediately, get some funding to build a prototype of the system? No, we first create it in a virtual environment to see how it would respond, get some information about how it would actually perform, and use that as a feedback to our system to help it learn and help it train and help it find an even more optimized state. So virtual environments for energy storage systems often include some physics-based simulation platform. They can pull from a linked data infrastructure for calibration and validation data, and when combined with an optimizer, really serve as a powerful means to evaluate and optimize complex systems. So in this talk, I'm going to highlight the role of physics-based continuum simulations for batteries and how they integrate with virtual environments. And I chose batteries because they have some of the most well-developed open source simulation platforms with broad user communities and really well-developed nice examples to work with, even though many of the same fundamental principles are valid for any electrochemical energy storage device like fuel cells or electrolyzers or supercaps. Very broad applicability. And I think it's important to keep in mind that when we talk about continuum simulations, or really any kind of simulation, there's a variety of level of detail that we can look into depending on what type of question that we need to answer and how much computational power we have available. So on one end, we may say we can actually resolve the entire microstructure in, particle level detail. And this is very helpful for looking at things like localized lithium plating, for example. But it can also be computationally expensive, especially if we want to simulate very large systems. So we can apply various model reductions to maybe homogenize, our microstructure as representative volume elements, or reduce it even further to just like a 1D grid across the thickness with a pseudo dimension across the particle, or even simulate it as a single particle model, either with or without an electrolyte. And each of these approaches are valid and useful for answering different types of questions. And this is something that's important to keep in mind for how these things will integrate with virtual environments when we want to do some kind of optimization. So when it comes to applying physics-based battery modeling tools in virtual environments, I think it's not always necessary for everybody to really, get all of the details of the implementation, but I think it's good to have a basic understanding of the legs that battery modeling stands on, because it gives you a good indication of what are this particular method's strengths and what are its limitations. And from my perspective, there are three basic legs. There's thermodynamics, kinetics, and transport. Now, thermodynamics tells us about the materials and the electrodes in the battery and why these things are able to store energy at all. And so that can tell us about things like the open circuit potential, the open circuit voltage profiles for lithium-ion batteries as a function of lithiation, and kind of sets the boundaries of the function of our device. Now, once we actually start drawing current, either through discharge or charging, kinetics starts to become very important. What kind of overpotentials are necessary to drive the reaction, and how easy is that to do in charging or discharging states? But electrochemical systems are extremely tightly coupled, and things like temperature and concentration and electric potential really matter. So we also need good descriptions for transport, either of charged particles like lithium in the electrolyte, or electrons in the solid phases, or temperature if we want to do non-isothermal simulations. So even though these models can, quickly take on a lot of complexity, the kind of basics are always there, and it's good to keep these in mind. So you may be relieved to know that I really didn't have enough time within the scope of this lecture to go through the equations that a lot of physics-based battery modeling tools are based on. But that's okay, because again, you don't need to panic. It's not really your job to set up and solve systems of differential equations, because there are a lot of really good open source frameworks for building and solving continuum models in a variety of languages like Python and Julia and MATLAB. And your job is to know that they exist and to help put them to good use. So let's have a look at some examples of how we can do that. So one such open source framework for doing electrochemical device simulation is called BATMO. And BATMO is the battery modeling toolbox that we created in 2019 and implemented in Julia and MATLAB for solving PXD-type Newman models with concentrated solution theory. And the thing that makes BATMO really special is that it works not only for small systems like single particle models and P2D models, but also for fully resolved 3D cell geometries with very fast solutions and a friendly web app user interface. And even though we developed Batmo with lithium-ion batteries at kind of the core of its function, we also designed it to be flexible, and we also use it for metal air battery simulations and AEM electrolyzer simulations. So Batmo discretizes battery geometry into a set of finite volumes where it can solve the physics-based DFN equations for transport and kinetics and thermodynamics that we've just discussed. And Batmo also makes it really easy to move between different orders of model reductions. So depending on the question that we want to answer, we may simulate a full 3D simulation of the entire cell, or we may reduce that down to a P2D model if we would just want to do some kind of quick optimizations. But either way, it makes it very easy to move between different levels of discretization and model reduction. And what this allows us to do is basically to look inside the cell as it's being discharged, as it's being charged, and find out more about what exactly is going on inside and how that might affect performance. So for example, this is a blade format lithium-ion battery where we can look at the gradient of electric potential, over these very long electrodes. And because everything is so tightly coupled, how does that affect things like lithiation of the active materials in the positive electrode or the negative electrode? And how does this change as the cell is cycled over and over again? Do we always get homogeneous lithiation, or do we start to see some gradients that build up within the cell? These are the types of questions that Batmo can help us answer. So just to drive that home, I think it's good to look at an example of a large format battery cell, like for example the 4680 cylindrical cell that's being adopted by many electric vehicle manufacturers. Because this is a system that's traditionally very difficult to solve. You need, millions of coupled partial differential equations, and that's traditionally been very burdensome. But new advanced tools like Batmo and others make it easy to set this up and solve in a relatively short amount of time. So for example, we can use Batmo to simulate how temperature profiles may develop in the cell considering different design choices. For example, the Tesla 4680 cell was famous for using continuous tabs or tabless design that reduces a lot of the heat hot spots within the cell and thus enabling faster charging. And this is something that we're able to resolve in Batmo, implicitly linked together with the electrochemistry on the same grid without needing co-simulation, even for very large systems. So if one factor limiting the use of physics-based simulation platforms in virtual environments has been the computational load, which, as we've shown, is starting to be alleviated. Another is the parameterization burden. These models are very complex. They require a lot of different kinds of parameters, and it's expensive to measure them or to determine them for every individual cell. But we're starting to come up with new ways of doing parameter calibration and optimization in more cost-effective ways. And what we see here is, again, an example of 4680 cell parameterization, where we've started with just some parameterization from literature in with the red curve here, and compared that with some experimentally measured data in the blue curve that we obtained from this resource in literature. And after applying our gradient-based optimization workflow, we're able to calibrate our parameterization and get very good fits to experimental data, also under different conditions, low C rate, C over 20, and high C rate, 2C. So even though you're never going to get around the burden of parameterization completely, we can start to leverage new advances in optimization and mathematics to try to alleviate that and facilitate it as much as we can. Now, the same kind of automatic differentiation method that we use to do parameter calibration also opens the door for gradient-based optimization. So for example, if we're looking for the optimum combination of mass loading on the negative electrode and mass loading on the positive electrode, instead of needing to simulate every single combination of these parameters and getting the whole cost landscape, we can start somewhere way off in right field, and because we have the gradients already, we can just walk up the gradient until we find our optimized combination and achieve in tens of simulations what would have taken hundreds of simulations if we wanted to do just by brute force. So this opens the door for doing good design optimization and parameter calibration within our virtual environment. Now, one of the guiding principles in the development of BATMO has been that we don't want BATMO to just be a tool for modeling people, but we want it to be accessible to everybody. And for that reason, we've created this online web app that allows users to go through in a relatively friendly user interface, build models of your cells, set different cycling protocols, and simulate what the performance is. And we can see here the simulations are very fast in the frame of just a few seconds, and we can already get our basic results from a P2D implementation of lithium-ion battery simulations. And here we can see, we get the cell voltage, we get the cell current, we can look into the states of concentration and potential in the different components, electrolyte, negative electrode, positive electrode, exactly. And also download the results to be able to share with other people or share in different databases. We can also go through and do some basic design modifications. For example, if we want to make the electrodes thicker and maybe change the porosity of our electrode to maintain a appropriate N to P ratio. Exactly. And we can also adjust the protocol and say, instead of simulating one cycle at 1C, I'm going to simulate 2 cycles at a discharging rate of 2C and a charging rate of 1C. And again, in the web app interface, we can make this comparison very quickly and see how those results compare to other simulations that we've run. So generally, we've made BATMO available to the community with the goal of making it a resource that helps support research and innovation and helps to make it efficient to reproduce and share simulation results. So I've been talking a lot about BATMO because that's one of the tools that we develop at Syntef and is what we have the most experience with. But I think it's important to also highlight that there are a lot of really good open source tools available for doing electrochemical simulation. One is PyBAM, which is a framework for solving single particle models and P2D models. And I think one of their biggest assets is that they have really excellent documentation, excellent examples, and a extensive user community. And because it's implemented in Python, there's also a larger ecosystem of tools like PyBop, for example, which also does parameterization and optimization. And many of these are available under open source licenses. So if you're interested in doing this kind of work and doing it in Python, I think PyBAM is a really great place for you to start. Another Python-based simulation tool for also doing higher level simulations like P4D simulations is called CityMod. And CityMod is based on the Phoenix platform for solving finite element models, and it's developed by CityTech research organization in Spain, and also available under an open source license. So again, another very nice open source tool, which is an asset for the digitalization community. So finally, to summarize on the virtual environments section, virtual environments are an essential part of the digitalization chain that allow machines to evaluate the effects of changes to complex systems and identify optimized states. And, physics-based simulation tools are one possibility to do this in an efficient and powerful way. And, I wish I had more time to go into more details of, alternative approaches, but I think, physics-based is a really good foundation to start with. And the good news is that especially for batteries, there are a lot of good open source frameworks available. So if you want to start integrating these into your systems, they're becoming easier and easier to use, even if you don't have the time to dive into the details of the mathematics or the numerical implementations. So finally, if you'd like to learn more, here are some additional resources where you can find information about Batmo, PyBAM, and CityMod, and hopefully find some combination of resources that is suitable for your needs and for your questions. To wrap it all up, again, I'd just like to highlight that when we want to move from digitalization to innovation, as much as we would like to have just one solution to rule them all, there really is no single silver bullet that will solve all the digitalization challenges in energy storage. Instead, it's the community working together, publishing data, building tools, and doing continuous improvement that's going to lead to new innovations and help us to establish a more robust and sustainable energy storage infrastructure. So I hope the main takeaway that you get from this lecture is that there are a lot of exciting opportunities, there are a lot of exciting tools, and there's a lot of possibility for growth in digitalization in the energy storage sector. And we hope that you will join us in building these tools and creating a vibrant community. Thank you very much for your time, and thank you very much for your attention. And thank you to the European Union, who has supported much of the work in this lecture, including projects like Battery 2030 Plus, Intelligent, and DigiBat.